We will now learn how to compute the derivative of a composition of functions g circle h of x. Recall that g circle h of x means g of h of x. Since h depends on x and g depends on h, we can see that g depends on x. So we can compute the derivative of g with respect to x. Using our definition, we can write the derivative as dg dx equals the limit as delta x goes to 0 of g of x plus delta x minus g of x all over delta x. Or in other words, the limit as delta x goes to 0 of the change in g over the change in x. This way of writing it will be useful in computing the derivative of the composition. As we said a moment ago, g also depends on h, so we can compute the derivative of g with respect to h. Using the same logic as above, the derivative of g with respect to h is roughly the change in g over the change in h. The final thing we'll want to keep in mind is that h depends on x, so we can compute the derivative of h with respect to x, which is that the derivative of h with respect to x is roughly the change in h over the change in x. Using that the derivative of g with respect to h is roughly the change in g over the change in h, and the derivative of h with respect to x is roughly the change in h over the change in x, we can compute the derivative of g with respect to x, which is the limit as delta x goes to 0 of the change in g over the change in x. We will now use some clever arithmetic to rewrite this. In particular, we'll multiply this by 1, because multiplication by 1 doesn't change a number. But the way we'll multiply by 1 is by multiplying by delta h over delta h. Because remember, anything divided by itself, including delta h, is just 1. Multiplying across top and bottom, we can rewrite this as the limit as delta x goes to 0 of the change in g times the change in h all over the change in x times the change in h. Pulling this fraction back apart, with the order switched in the bottom, we have the limit as delta x goes to 0 of the change in g over the change in h times the change in h over the change in x. But the change in g over the change in h is roughly the derivative of g with respect to h. And the change in h over the change in x is roughly the derivative of h with respect to x. So this is the derivative of g with respect to h times the derivative of h with respect to x. So finally, we have that the derivative of g with respect to x is the derivative of g with respect to h times the derivative of h with respect to x. We will refer to this as the chain rule. Let's now use the chain rule we just found to look at an example. Say we have h of x equals x cubed minus x, and g of h is h squared. Then we have g circle h of x is x cubed minus x all squared. Now to compute the derivative of x cubed minus x all squared, we can break it down as the derivative of g with respect to h times the derivative of h with respect to x. Using the power rule, we get that the derivative of g with respect to h is 2h, and the derivative of h with respect to x is 3x squared minus 1. It is undesirable to have our function in terms of two variables, h and x. But we can replace h with x cubed minus x, since h of x is x cubed minus x. Doing this replacement, we get 2 times x cubed minus x times 3x squared minus 1 as the derivative of x cubed minus x squared. Let's now look at the chain rule with the function x squared plus 1 to the 162 power to compute its derivative. Here, we're not told what the composition of our function is, so we need to find what g and h must be. This is typically the hardest part of a problem like this. To find the composition, we need to think about what happens to x first. Inside the parentheses, first we compute x squared plus 1. So our inside function h is the function h of x equals x squared plus 1. We then need to think about what happens to our function h, which is x squared plus 1. In this example, we take x squared plus 1 and raise it to the 162 power. So our outside function, g of h, is h to the 162, since we raise x squared plus 1 to the 162 power. Now that we have our composition, we can compute our derivative of g with respect to x. Using the chain rule, this is the derivative of g with respect to h times the derivative of h with respect to x. So to carry on, we need to compute these derivatives. Using our power rule, we have that the derivative of g with respect to h is 162h to the 161. And the derivative of h with respect to x is 2x plus 1. As we did in the last example, we want to put this all in terms of x, so we need to replace h with x squared plus 1. For our final result, which is that the derivative of x squared plus 1 to the 162 power is 162 times x squared plus 1 to the 161, all times 2x plus 1. Let's look at one more example. Let's look at the function e to the 3x minus 1 and compute its derivative. Again, since we're not given the composition, we need to find it. Here, the first thing that happens to x is that we multiply by 3 and subtract 1. So our inside function h of x is 3x minus 1. We now need to think about what happens to 3x minus 1 in our original function e to the 3x minus 1. What happens is that we raise e to that power. So we have g of h is e to the h. So we now have our composition, which is that we can write the function e to the 3x minus 1 as g of h of x, where h of x is 3x minus 1 and g of h is e to the h. Using this, we can now compute the derivative of g with respect to x, which by the chain rule is the derivative of g with respect to h times the derivative of h with respect to x. We can compute the derivative of h with respect to x using the power rule to get 3, since the derivative of minus 1, our constant, is 0. Then, computing the derivative of g with respect to h, we have that the derivative of e to the h is simply e to the h. So we can write dg dh times dh dx as e to the h times 3. Finally, as we did before, we want to write our function in terms of x rather than h. So replacing h with 3x minus 1, we have e to the 3x minus 1 all times 3. So in conclusion, we have that the derivative of e to the 3x minus 1 is 3 times e to the 3x minus 1.